Good evening, ladies and gentlemen. I'm glad to have Professor Mohammed Hadi with me today, and he accepted this invitation. He will be presenting some of his Ph.D. students' work regarding self-compacting concrete reinforced with steel pipes. It's an interesting project, and we will learn a lot of things from him. Professor Mohammed Hadi, he is an academic program director, civil engineering schools of civil mining and environmental engineering, University of Wollongong, New South Wales, Australia. And I know him since my childhood. He's one of my relatives in some way. But he's older than me, of course. I think you aged 67 years now. I'm only 60. Professor Mohammed Hadi has long research background in structural engineering, in particular in the areas of concrete structures, strengthening structures, and the use of novel materials to reinforce the structures. I think he already successfully supervised more than 40 PhD students, and he has already continuing with 10 PhD students nowadays. He published more than 320 papers, enormous number, incredible. And he also has 2 patents. Professor Hadi got his Bachelor of Science with honors degree in 1977 from University of Baghdad, College of Engineering, Department of Civil Engineering. He continued his master's degree from the same department, and he got the MSc in 1980 in structural engineering. He moved to United Kingdom to get his PhD in 1989. He returned back to Iraq in Baghdad, and he served as a university professor for a long time. In 1992, he moved to Australia. 1994, he started his position as a lecturer instructor in Wollongong University, and he continued there till today, until he became, of course, a full professor last year in 2022. I'm very happy to see you again after all this time, and I'm sure everybody will enjoy your presentation. I know how much knowledgeable and a perfect engineer and a professor you are, Professor Hadi. Welcome.
Thank you very much. I appreciate this introduction. Actually, we both went to the same university, and we grew up in the same suburb, besides being relatives, so it is good. And we are both civil engineers. I worked a little bit, about 9 years in soil mechanics, geomechanics.
Oh, I didn't know that.
So I know a little bit about confined and confined triaxial consolidation, but I left above ground later. So Dr. Mufty told me, I told him I want to wear a jacket. He said, no, tie. He said, why not jacket? So today is 3rd of May, and believe it or not, the temperature is beautiful in Sydney. It is 25 centigrade. We are now at the end of autumn. So Remember,
we are in the end of
yes,
winter.
we
We
are
are in
at
the
the
north
end.
part of the globe,
Yes,
and you are in the south part.
south.
What are we going to present, Doctor, today?
Okay, just a couple of things before I start. Wollongong is 80 kilometers south of Sydney. Indeed, I live in southern suburbs of Sydney, and I drive 60 kilometers to the university. University was established 1951. So it is not very big university. It has full engineering and medicine and science and the like. About 33,000 students. Okay, enough about this. It is on the coast, so it is on the water, Wollongong. Enough about this.
Did they open a branch in Dubai or
actually in
UAE?
Dubai 30 years ago? It was the first university, foreign university in Dubai 30 years ago.
And it's still serving,
going.
still there.
Still going. And they have civil engineering and they have other engineering.
Because I remember I saw the name some way when I was in Dubai.
I'm also the academic program director of Dubai. So, I liaise with them. There is another guy so I work closely with them. And our degrees are similar, are the same, Dubai and us. So enough about this. Dr. Al-Mufti was kind enough to ask me for this presentation. So I said, okay, let me do two things. The first one is to show you the model of PhD based in Australia. So it is slightly different than US, than Canada. It is similar to the UK model. So it's only maximum 3.5 years of research in one topic. So I'm going to show you the work of one guy.
Do they have courses before the research?
No, it's only research. Pure research.
But what are the prerequisites for the PhD program?
Either first class honors, meaning more than 77.5 average mark in your bachelor's, or master's after the bachelor's. Okay, so it is similar to the English. I'm aware of the UK model.
Yes.
Anyway, so the reason I showed you this, the amount of work that a PhD student has put in one PhD. So this is the reason I'm showing you this. And the second thing is the technical aspect. So, but the main thrust of this presentation is the amount of work that a PhD student can show you. Can I start sharing?
Yeah, you can share always.
Okay. So if I go here and I start sharing, sorry about this. Right. Now, so the student that I had was Faiz Al-Husseini, and he did PhD under my supervision, and his co-supervisor was Associate Professor Niaz Sheikh. So most of the work that I'm presenting is based on the work of Faiz, and we published this work in several good international journals, including ASCE Structures.
How many papers, Professor?
I think 4 or 5 papers.
Whatever.
8 papers.
I would like to have their names, titles,
I will do that.
Application details.
I will do that.
We will put them in the description of the video.
I will do that.
Of the discussion, so that everybody can have access to it. Yeah.
And some of them, they have access through Wollongong Library. I'll send you the link as well. Now, let's look at the at the end, I'll show you a couple of slides about a different thing. Now, that one was done in collaboration with another PhD student. His name Hassan. Haider Hassan. So most of the work is Faiz.
So even your students, these students are also from Iraq.
They are Iraq, yes.
Yeah.
Sorry, I detour. I have had students from Indonesia, from Turkey, from Jordan, Vietnam, China, Iraq, Pakistan, India, Bangladesh. Did I miss anything?
International research.
Australian, of course. Now I have one guy from Belgium. So I always tell my students, you are my friend if you are working hard. So the prerequisite is working hard. So let me show you what is this one. I had a meeting with industry, and those guys are steel manufacturers. Sorry, I just go back. Wollongong, yeah. Wollongong is the city of steel. So it is city where there are iron ore mines. Sorry, coal mines. So Wollongong has a lot of coal. Western Australia, which is about 4,000 kilometers west, they have iron ore. So they ship iron to Wollongong, to Port Kembla, and they manufacture steel. So it is very big. BHP, Broken Hill Proprietary Limited, very big company in the world. They manufacture steel. And there is big mill, and they do all this, and they produce slag. So Wollongong is the city of steel in Australia. So the guy that I was an engineer, materials engineer, we were sitting, and he said, we produce tubes. And I said, why don't we use these tubes in columns? So this was the idea, to use the tubes in a different application. So we said, okay. Then Faiz came. And Faiz, his background is more concrete technology. I said, Faiz, can you do, because the tubes are small, we cannot put normal concrete. If we put normal concrete, there will be segregation. I said, Faiz, can you do self-compacting concrete? And the man said, yes. So this is the birth of the idea. So the title, it is columns, concrete columns, but reinforced with steel tubes, and you have self-compacting because we don't want segregation. So this is the idea of this. Don't worry about the objective. So it is using different type of reinforcement, and to see whether it works or not. Now, I don't want to bore you with these details. We have been using, tension, compression. We have been using reinforcing bars many years ago, maybe more than 100 years ago. But the idea is here to use these tubes. Why? You will have the concrete will be confined concrete. So when you have confined concrete, then you will have better properties. Better properties, the compressive strength will be higher. Also, the ductility will be higher. So this is the idea that we are relying on, to use different type of reinforcement. Now, self-compacting concrete was started about 40 years ago in Japan. So what is the idea? It is just you put the concrete, no vibration, no compaction. You just put concrete and it flows. and then you leave it for whatever, 28 days, and that's it. So this is the self-compacting concrete. And the idea is we will have confinement. I'm not going to bore you in details, but in general, we have ties or helix. Americans call it spirals. It's the same thing, but spiral, from English point of view, the diameter goes smaller. So helix is the proper way. And as you reduce the spacing, the confinement increases, then you will have better behavior in concrete. Now,
So is the helical reinforcement also made of pipes?
no.
Okay. So what makes the concrete self-compacting?
Yes, I will come.
Okay.
I'll show you the mixed design.
Okay.
Now, before we started, whenever we do the test, we do preliminary test. Preliminary test includes all materials. And all materials meaning you have the steel. We do all the testing based on Australian standard. If there isn't, we go to ASTM, Canadian or European standards. But if there is, then we have
You have to follow those
we
criteria.
follow all the materials.
Yeah.
And this is the nominal 500 MPa for the steel, for the deformed steel, 12 millimeter and 60 millimeters. For the steel tubes, they are 350. So we came up with this idea. How can we come up with this? Again, I don't want to bore you with numbers. I want to tell you about the concept. So then we said, okay, let's see what are the tests that we can do on those. This is materials. I will start with the lower two rows. These are tension. So we said, okay, let's do the tension, 12 millimeter, 16 millimeter bars, and for the steel bars. Then we said, okay, compression. Now for the compression, we did for the solid bars. Then we did for the tubes, empty and filled with self-compacting concrete. Now, because you have in tension, there is no problem. You have one length. Whereas when it comes to compression, there is the problem of buckling, pi squared di over L squared. But because you have this problem, then we had different what's called L by D ratio, length to diameter ratio, and to see what is the effect. And then we did those empty and full. So you can see this preliminary testing, you can see the size of test. You have, I don't know, maybe 70, 80, and of course we repeat everything 3 times to have the average. So this is the idea. Now let's go back to the self-compacting. Now in self-compacting, cement is not more. Then we added some minerals, fly ash and the like. Then the main thing, the coarse aggregate is small, whereas fine aggregate is large. Coarse aggregate, 10 millimeter maximum. This is what we use because of the size of our samples. Then we had some high range water reducer and water powder. So we started, sorry.
What is that water reducer?
High range water reducer, like super plasticizers.
Oh.
We buy them. We buy them off the shelf. Okay. So we bought all those. And now you can easily say that this is self-compacting concrete. Then I said, okay, what is self-compacting concrete? And I'm going back to show you. Now we haven't started the main testing as yet. We are talking about the basics, materials. Now, how do you know that this material is self-compacting concrete? There are slump flow. And we need to put this, leave it, and read the diameter, and to see the slump flow of the material. This is easy, but there is more. The more is
Why the slump cone is reversed? Why it's upside down?
this is the self-compacting concrete is like this. I know. The self-compacting concrete, the slump is like this. It is not where bigger to smaller. It is this way. And there we measure the height, right? With the slump, we measure the height.
Yeah,
Whereas
the
here we are
usual slump is how much
reduction in height.
reduction happens in height.
Whereas this one is the flow. So it will go, we read the diameter. We leave it, and then we read. So this is one test. The second test. Now I will show you. You can see this J-ring. This is what we built. We didn't buy. So we built this. And basically we built it from steel, and we put this jig and this J-ring, and we did all those pins where their diameter, and then we leave and read the diameter, and to see the passing ability. So this is the second test, to see we have self-compacting concrete. And the third one is column segregation. Again, it is based on ASTM.
Do you use this slag like GGBS or?
We use slag, yes. It's normally if you go, I mean, shops, and there is always fly ash and slag.
Okay. Do you do special trials for different percentages to know, for example, setting time, strength, or you
yes.
you have guides already for designing your?
Yes, can I get back to you later on this particular one?
But don't forget it.
No, I will not.
Okay, I'm interested to show to people what is the self-compacting concrete and how we deal with it.
So the self-compacting concrete, this was the mixed design. And then we did the slump flow, we did the J-ring, and this is the last test to see the column segregation. And again, what we built all those. So all those, this is one PhD student. I'm talking about the work of one PhD student. And this is before starting his work. And he did all this test. So, and then the segregation, and to see that it is passing, it is part of, it is self-compacting concrete. So we finished this one. Then we have the compression test. This is normal. We use small cylinders, 100 mil by 200.
Why do you use a small?
Australian standard says 100, or we can use 150. But is
it related to the size of the aggregate in some way?
No, it is handling. It is less material and handling, lighter in weight. So usually in Australia, we use the 100 mil. Okay, so all this is normal. For the steel bars, what we did, there is something called like potentiometer, like strain gauge. We attach it to the top and bottom. Its length is just over 100 mil. It is in inches, so 106 mil. And then this green that you can see is connected to a data taker, and then it goes to the computer, and it will give us the load is from the machine, the compression machine, tension machine, and the elongation for this gauge length, it will give us the change in length. And we can determine the strain.
Usually these kind of measurement tools, whether strain gauges, as long as it is kind of uh, checking or recording the change in the resistivity, I think we should calibrate them before usage.
You are 100% right.
Yeah.
The first thing what I liked in your comment is you said resistivity. Of course, as engineers, and I mean, when first time I used, okay, strain gauge. What is strain gauge? What does it do? There is V is equal to IR.
Yes.
So V is the voltage, I is the current, R is the resistance. But if the length increases, V is constant, I will change.
I
And from this,
decreases and resistivity increases.
so
Yeah.
this is what I like in our generation. We go back to basics. And of course, we calibrate. We calibrate. Of course,
we need to calibrate. Yeah.
We calibrate all our machines, compression machines, we calibrate them every 6 months. We have different machines for compression, so we calibrate them. And then every year or so, we take those machines outside. So there's a company that calibrates our compression machines for testing. So everything is calibrated. And
in strain gauges, we need to calibrate the strain gauge itself.
We do.
Also with
that
temperature.
Is easier.
Because temperature also affects the results.
We do that. Correct. 100%. Thank you. So this is.
I just want to highlight things that maybe you just pass over them as
there are lots of things behind the scenes. There are lots of things behind the scenes. And thank you.
Every step you do, maybe it has a lot of preparation before and after, maybe. Yeah.
Correct. Okay, so this is now when it comes to bars, it is easy. We have this machine. It is 2 meter head length. So it is a beautiful machine, tension compression, only 50 tons, so 500 kilonewtons, but 2 meters. So we don't have problem with length. So we grip these steel bars, pull them, no problem.
So doctor, this photograph shows 2 meters?
No, this is only less than half a meter.
Okay.
But it can go, this machine.
Yeah, you can have longer pieces, yeah.
Longer. Now, when it comes to the bars, it's easy. But when it comes to tubes, if you grip the tube, it will collapse. So then we went to ASTM, and then we have, on the left-hand side, you have the metal plugs. And we built the metal plugs. We used the lathe, and we created all those metal plugs. And the idea is we put one metal plug at the top, one at the bottom, and then we grip them.
Yeah.
And then we test them.
It will strengthen the tube at the top and the bottom.
So
but in the middle, you will keep it empty so that you will have normal stress strain relation for the pipe itself.
Correct.
Yeah.
So you can see the amount of work the student is doing for this. For compression, it was easy. So we tested them, compression, different length.
You're talking about the pipes.
Pipes.
Okay.
Compression. No, the first photo on the left-hand side is steel bar.
Oh, yeah, that one is for steel bars, yes.
Then the second one is steel tubes. And the third one, steel tube and full with concrete in compression. So this is the steel bars. So we put them in compression. That was easy. And you can see, I love buckling. This is what I teach buckling in second year. And then you go to...
I like when you say, I love buckling.
I love buckling.
I don't love any failure.
I don't love... Well, the worst type of failure is buckling. The second worst.
But that's the way we learn. From failure, we learn
failure.
What to do.
Yeah. And you can see here, I don't know whether you can see it, they call it elephant foot. When the metal starts crumbling, so they call it metal elephant foot. So here we tested those in steel tubes, empty, and we did them in full with concrete. Actually,
you will not have that elephant foot when it is filled, right?
Correct. Yes. And these are some results. Again, the focus is on amount of work one PhD student is doing. Remember, all this is this preliminary testing.
So most of these tests, Faz did them.
All of them.
Yeah.
Oh, up to now, and I'll show you more. So this is for tension, for specimens. These are
and these are published already.
They are published.
Okay.
They are published already. Okay. Now here you can see we are comparing the N12, which is the deformed bar, with the 26.9 tubes.
This N is referring to an Australian standard?
N refers to deformed bar.
But an Australian standard.
Australian standard with nominal tensile strength of 500 MPa. The N is...
You know, we use phi for diameter. We use the capital letter T for diameter, especially in UAE and Saudi Arabia. We use T. In Iraq and some other places we use phi. Maybe in India, I'm not sure. In US we use number. So there's a crosshatch for the number of the bars. It's interesting. We the community of engineers for many decades we decide one way to define the bars.
About 25-30 years ago, the steel in Australia was 400 MPa. Then they moved from 4 to 500.
Yeah, so also the British standards now, it's 500.
So
the BS 4449 was before 460 MPa and changed to 500 MPa.
Yes. So what happened?
But in the West, in US, in the United States, we're still having 420 or 414 MPa.
So what happened when they moved from 400 to 500? The problem was ductility. Then they ended up with 3 types of steel bars. N is normal ductility. L, letter L.
Oh, so the letters are for ductility.
L is for low ductility. For example, if you have a driveway slab on ground, really you don't need the high ductility. Then most of our standards are with New Zealand, and New Zealand are earthquake-prone country, so they need all their bars with high ductility. So they have E. So L, low ductility, N, normal, and then you have E for severe conditions, earthquakes. In Australia, most of the work that I do is N. Most of the buildings are N. Okay, sorry. But I agree with you.
I'm interested in this also. In fact, what makes the bars more ductile or less ductile or high strength or low strength is
Carbon.
the additives or the
additives.
The other materials that are added, material that is added to the steel. So
Correct.
mainly is the carbon, then the other,
yes,
like other things like copper, nickel, whatever, oxides maybe. So it's not a simple thing to get a
no, it is
specific
not.
strength and a specific ductility. But manufacturers get used to it because after testing they know, and usually the values of the yield strength, which comes with the trade mill, with the not trade mill, what do we call it?
Steel mill, yeah.
Steel mill. We call it the steel mill. Yeah. The steel mill or the manufacturer.
But
List.
I have to say that for the last 30 years, I'm testing all the steel bars.
Yeah.
And always they are above 500.
Yeah, they're always above. They're always above. Yeah.
Which is good.
In more ductile steel, I think you will find the ultimate strength is long way after
from the yield.
Yeah. That gives the ductility its meaning. Yeah.
So here you can see, although it is material testing, we put load deformation. The reason we did this, we are comparing what is the capacity of the bars and equivalent area of bars, of tubes. And likewise, N16 with the bigger tubes. And it was good. Then this is, we look at all of them to see what is the N12s. This is for, and then these are the empty, and this is for the concrete filled.
So the concrete filled seems to be
compression. Yes.
Yeah, it seems to have a higher strength.
Yes, and this is for L/D ratio 4.
Oh, so long, very long specimens. These ones.
No, 4. So not much. It's about
no. Usually,
so it's 100 mil.
Usually, it's two. So height to width is usually 2. So when you go longer, you have less strength.
Yeah, but still, it was better than the N12. Then we continued.
Yeah.
This is for the other bigger.
These are also compression, yeah.
Compression. Then we continued. This is for, I don't want to bore you. It is obvious as we increase the L/D ratio, we will have less. So this is L/12, L/D 12, which is this one. You have much less strength.
You made compression tests on length to diameter ratio of 12.
Yes. From 2.
This usually cannot stand for concrete, but because there's a steel this way.
This is only steel and filled with concrete.
Steel may hold such length to diameter ratios. Yeah.
Correct. And remember, this is 33 or 25, so it is only this much, about 1 inch, the old system.
Yeah.
And this is for the. So all this so far, I've been talking, this is all the preliminary testing that Faiz did in preparation. Remember, he did all the self-compacting
he should
concrete.
Identify his material, of course.
And he built the self-compacting, the testing for self-compacting concrete. He built the plugs for tension, for compression, all those he did. So this is the amount of Ph.D. This is before starting the testing. Now the testing,
Professor, how about the thickness of the pipes? How much is that thickness?
thickness, not much. It is 2-3 millimeters. Okay. Now here we did the testing. Now these testing I'll show you. Because of our compression machine, 500 ton, it is about 1 meter. So we don't test more than 800 mil. So we said, okay, let's test those into 5 groups of specimens. The first group is just reference specimen. And here we have the N16 and 6 of them, and then R10. R10, this is the 250 plain bars for helix. And R10 spacing 50 mil. Then we said, for the remainder, these are all tubes. Ties are the same, are 10, but we have the first 2 groups, group 2 and 3, you have 33.7, 6 of them, 4 and 5, each 6 of them, 26.9. Then we change the helix spacing either 50 or 75 mils. And the diameter 240.
I don't know. I don't know if you have checked the design of the helical reinforcement, whether it will provide you with a spirally reinforced section, or you should assume these as tied reinforced sections. Whether
no, they are spiral.
You have enough confinement.
There is enough confinement. Based on ACI, it is 50 mil. If we go above 50, there will be problems. So 50 mil is the minimum based on ACI, and this is what we do.
It's the maximum.
Yeah, maximum.
Is the maximum for confined column.
Correct.
Yeah, but you have here 75. And
75 because we are using different pipes.
Okay.
So we said, okay, if we go above, what will happen?
Yeah.
And
the ratio of the longitudinal reinforcement
is within the 1:4 based on ACI. They are based on
when we are calculating the percentage of reinforcement with pipes, you will use the thickness multiplied by the diameter, so you divide it by
net area times 6, and you can see in this column. This column is
how we will distinguish in design between designing with deformed bars and designing with smooth pipes.
Of course,
good question, right? Good question, this one.
Good question. Good question.
Yeah.
I will get back to you. So this is the second one.
Yeah, we have two questions now.
Okay, so we have 5 groups. And the first one is just normal reinforcement. Second, the ST, the 37.5. And 37.5 spacing of helix 75 mil. And the last one, 26.9. Now, each group of specimens has 4 specimens. The first specimen, we tested it as in concentric load. The second one under 25 millimeter eccentricity. Third one, 50 millimeter eccentricity. Last one was flexural, 4-point bending. So you can see we have 5 times 4, 20 specimens. Now for the reinforcement ratio, we try to keep them the same. And for the lateral reinforcement ratio, you can see there is difference in between them depending on the spacing. So we took all those into account. Now, another
This percentage is by volume, of course.
by volume.
Yeah.
By volume. Now I'll show you another trick here. So the first drawing here, these are PVC pipes. So when we design, we go and see what is available in the market for water or for whatever. And this is one of the constraints. What is available, internal diameter, and we use them. What is the trick? We take them 6 meters, cut them. When you cut them, you need to make sure that they are 100% square. We had a situation, not in this work before, where there was an apprentice and he put the pipe horizontally to cut it in the machine. And of course, it bent. And then he cut the pipes almost square, but not
Which
square.
part can you show, put your cursor on it? The point.
So here we are cutting it.
Oh, this one. Okay. It's
So
so
when you
small. I didn't see it.
So when you cut it, it is easy. I can cut it, but of course, technical officers, they do it better than me, better than I do. So you have to put it dead horizontal without any movement. So when you cut it, you have dead square. Just a trick. So this is easy, timber, easy. Now, usually in construction sites, and most of the work that I do, we put the reinforcing bars and finish. Now, we had a technical officer. He's from Switzerland, and he was a watchmaker. And he looked at this, he said, no, we cannot do this. I cannot maintain the exact spacing. I cannot maintain the positions. So he went and he built templates. He built templates to place the bars and the tubes in exactly the same location, required location. So this one was for the bars, and the other one is for the helix. So he wanted everything like a watch. And as you can see, these are the templates, and this is the outcome. I'm showing you few things which are behind the scenes.
It's nice. It's very neat. Very
neat.
Precise.
As I said, the man he's from Switzerland, and he was a watchmaker. So the precision, and we go with, all our technical officers are steel makers. So they go with micron. But this guy, no. He wants with nano. And then we placed strain gauges. And we put usually strain gauges in the bars. Strain gauge for us is about $10 per strain gauge. And we tell them, why do you want the strain gauge? What will you do with this? Anyway, this is a different story. So we placed the strain gauges on the longitudinal bars, 2 of them in opposite sides. And when we test them, especially in eccentricity, we know. And then we put smaller strain gauges to determine the confinement.
Well, yeah, here, this we can see the other one is fine. Yeah.
And the other one, we put
I want you, Professor, I want you, if you don't mind, to explain why do you have strain gauges in both directions, horizontally and vertically?
So vertically is easy for 2 things. If it is concentric, then we can determine the strain in the steel and then multiply it by modulus of elasticity we can see the stress in the steel. This is for the longitudinal bars. And then from this, we estimate the share of the load in the steel bar or steel tube, and the remaining load will be carried by the concrete. So this is for the concentric. Again, longitudinal. For the eccentric, you can determine the strain at the top and at the bottom. This is eccentric. It will work like a beam. So there will be the neutral axis. You can determine the location of the neutral axis. So you can work on this. So you can see, look at it as a beam. We are reading the strain at the top, compression, strain at the bottom, tension. And then from this, you can see the strain distribution. You can find the neutral axis, and you can determine, you can draw the capacity of this specimen in flexure. So the longitudinal, we have, if it is compression, we'll have the share carried by the steel, and the remainder will be carried by concrete. For eccentric or for flexure, it will act as a beam. We can see the strain at the top.
Yeah. For the first site, I thought it's for temperature, but I think it's inside the concrete, and maybe there's no need to
temperature
for
here.
the temperature changes. But
no,
anyway, the whole laboratory should be temperature controlled at least.
We are most of the time 25.
Yeah.
But for the lateral, for the horizontal strain gauge, this is for the expansion of the steel.
Because we have a pipe, it's not a normal steel.
Correct.
Yeah.
Yes.
The pipe may expand or shrink. Yeah.
Yeah.
Okay.
Then, after all this, we were able to buy the concrete. So we didn't need to do our concrete. We did all this testing, and then at the end, we bought the concrete, ready-mix concrete. And what we do, these are the empty, these are the specimens. And of course, we do compression, we do 4-point bending for flexure, we do splitting, Brazilian test. These are the bigger 150 cylinders. And this is what my group, we have developed to apply. The 4-point bending is easy. So we have all those, we apply the load, and we measure the deflection. They call it laser LVDT.
Yeah.
They call it triangulation, laser triangulation to measure the distance. And for the...
But it looks like you did not do this horizontally. Did you do it horizontally? I mean, the specimen was horizontal.
This one horizontal, yes.
Then why it's vertical on the side?
So because there are 4 specimens in each group. So one of them will be compression like this, and it will be without eccentricity. Then we can move this location.
I don't understand. Is this vertical or horizontal?
Okay, so we are talking about column specimens. These are
vertical.
Vertical.
So it's not related to the other group, which is 4-point bending.
So yeah. So in each group there are 3.
It's just
will be tested. They are
the
close.
The figures are mixed together. So
yes.
I thought it's explaining the other one.
No.
Yeah. Okay.
No. So 3 of the specimens will be tested as columns, 1 as beam, and these are our loading heads. So we tested those. And
what day you test after the casting?
28.
28.
Sorry.
And did you do crushing tests on the concrete with days, for example, 7, 14, 28, 56?
Okay, so what we do in general, we do 7 and 28. We don't do 14, we just do 7 and 28. Then, because they have here in this program, we have 20, there are 20 specimens, so no way we can test them in one day. We maximum test 2 to 3 per day. So what we do, we test in compression 3 cylinders the first day of testing, and then we do another 3 at the last day of testing. So when we pour the cylinders, we always add 6. 3 in compression, first day of testing, and 3 last day of testing.
But you don't have the development of strength with time.
We have 7 days.
7 and 28.
28.
Yeah, sometimes you know what makes me confused. Sometimes in 56 days, we may even double the strength. So,
yes. So for high strength concrete,
yeah, if the evolution of the strength is rapid, 1 day, 2 days, 3 days after the 28 may make difference.
Yeah,
that's my concern.
Totally agree with you. And for high strength concrete, I go with 7, 28, 56. But for this, which is normal concrete, sorry, let me go. For all our testing, we do 7, 28, first day of testing, last day of testing. For high strength concrete, we add another 3 at 56. And at 28 days, we also
What do you mean by first day and last day? I did not figure out that one.
Because last day and first day of testing, because you have 20 specimens, we cannot test them in one day.
So sorry, you have then a control on the strength evolution at the end of testing, because, for example, maybe it's 32 days.
It won't be 32 days. Maybe it's 2 months.
Oh,
because it takes time.
So
testing
we already reached 56.
Oh, yeah. Sometimes it's 2 months. By the time we finish, because we are not the only.
Because you will know how much strength difference you have between the specimens in the beginning and the specimens at the end.
Exactly. Remember that he's not the only PhD student. So the lab, they have their own restrictions.
With many, maybe.
There are others who are using the technical officers.
So they take the line for testing.
There's a queue, of course.
There's a queue.
So for the 7 days, 28 days, these are small cylinders. Priority, they don't take long. But for the big specimens, every specimen takes 2 to 3 hours testing, because I don't want to bore you. They are all displacement controlled.
Yeah.
They are displacement controlled. And then placing those specimens, they are 200-300 kilograms. So there is forklift, brings it, makes it square, and they start the testing. Start testing, force controlled.
Of course, it's difficult to hold them by hand. You need a machine, because 800.
And then you need to cap them.
Yeah.
You need to cap them with a high strength plaster and leave it in the machine to set, and then you start testing. So it takes 3 to 4 hours each specimen. Anyway, these are the details that I wanted.
No, but it's important to know these things. For me and the audience, it's good to know what's happening beyond the scene. Yeah.
Yes. So these are the results. You can see the buckling. There's the rupture of the ties, followed quickly by buckling. And then these are the...
So that figure was for the pipes, huh?
Yes.
Is this for a pipe?
This is for deformed bars.
This is for deformed bar. Okay.
And this is pipe. And here, there is no buckling as such, but there was tie failure. You can see the tie failure. And we continued. I don't want to bore you with all this.
No, I like to see them. It's fine.
Okay. So there's tie failure, but less buckling.
These ones are black. You have some of your pipes black and some are stainless steel or what?
No, they are all galvanized, but the light.
Oh, maybe
direction of
light,
them.
yeah. Okay.
And all those, you can see the spalling of the cover after a while. Here, there is a little bit of spalling, of buckling. And we continued, and these are, again, the tie. Again, from my experience, we had one guy who was licensed welder, but he put spot welding on the ties, and we had problems. So make sure that when you weld the ties, you weld them properly, because no way you will have the ties for 800 mil. It is very long. So it will come, we send it to a company, they do it for us, but then we bring them and we weld them, the ends. So you need to make sure. And this is the load deformation curves. This is the steel, this solid one. And you can see the strength is almost the same, but what was gain in ductility for the steel ones. These are for the compression, concentric, and these are the failure modes. Now, I promised Dr. Mufty two things. The first one, now I'll tell you, of course, there is more work I didn't show you. It is getting 5 p.m. my time, and I think it is 3 a.m., Ahmed, in your time, 2 or 3 a.m.
I'm enjoying the presentation, so
Okay.
I don't know what time is it now. Yeah, it's around 3 a.m. It's fine.
Okay, sorry. So this is the failure. Now, we had a problem, and I will tell you about the problem. Bond. There was failure in the bond. So what we did, we had to dig the concrete and add washers and weld them. And then add concrete, wrap with FRP and test. So now it is in my database. Bond is important. Now, the second thing that you asked me, Doctor.
This was the answer for the smooth pipes.
So the smooth pipes.
Yeah.
So
now
you need
the
to make
second
sure.
one is about the self-compacting concrete.
Self-compacting concrete. This one, we played with the self-compacting concrete, and ultimately we didn't mix the concrete in the labs. We bought the concrete from a company. But we use slag a lot. We have had, I think, more than 10 PhD students who did geopolymer concrete. And usually it is fly ash. And we start with activator and heat. Now, what we did, we said, okay, if we add slag, then we can cure it at ambient temperature.
Oh, we did not talk about the curing. Never talked about the curing.
Curing, this is normal curing. What we do, leave it for 1 day, and then we put Hessian for those ones, leave them for about 10 days, and always there is Hessian, wet Hessian with plastic bag, plastic wrapping. After 10 days, 15 days, we take them out of the molds, but we keep curing them. But for the cylinders, we put them in the curing tank. Okay, so for the geopolymer concrete or alkaline activated concrete, we do them with slag and fly ash to have ambient cured. Okay, so all this work was done by one PhD student. All this work was done by one PhD student, and I think he had 7, 8 papers. I'll send it to Dr. Mufty later. Now, the last part of my presentation. I had another student. His work is different. His work is different. His name is Haider Hassan. His work is different, but Faiz and Haider came and they said, well, we want to propose a method, direct method, to determine the tensile strength of concrete. The problem with concrete, of course, what we do the Brazilian test, the splitting test, indirect test. And I was surprised because when I was doing my PhD in the 80s, people were working on it, the gripping of concrete. The problem is gripping of concrete. So this is what they came up with. And in effect, they put some bars and they welded pins on them. So this is one. And in order to ensure that the failure is in the middle, they put like notches. They are 20 by 1 by 10, 20 by 10 notches, prisms. And they put all those. And this is all the detail of the pins. And the problem is, because you are dealing with material which is very weak in tension, and there are some problems, and we wanted to have perfect alignment. So we built universal joints, and those joints will adjust themselves. And you can see we are testing in the same machine, the 2-meter high machine.
Yeah.
And we put those and we tested them. We published this work in Construction Building Materials. And then we said, okay, let's send it to ASTM journal to tell them that we have this, and we actually published it in
It's really interesting. I would suggest that somebody should do some finite element analysis for crack propagation.
Yes.
Stress concentration in the what did you call that? Things?
Notches.
Notches.
Universal. Yes.
Near the notches. Yeah. What?
The failure was good.
I
because
mean
you can see
that at the
universal joint. Universal joint.
Can you show the other one, please? The other slide. This one. Yeah, these 3 pins.
Yes.
What do you call them?
Pins. We just
small
bars, and we welded
these
them.
pins will concentrate some forces on the concrete.
They will. But our estimate should be negligible compared to the strength of the steel. Remember, this is 250 MPa, and concrete is maybe 5 MPa.
Yeah.
5.
I'm not worried about the steel. I'm worried about what's happening in the concrete in these areas.
Yes.
But because of the notches, because of the...
We are forcing them to break at that.
Yeah. You're making in the middle...
The area is smaller.
Smaller area, yeah. That will cause the stress concentration to be there. And how much? Can we know?
Less than 10%, but we were able to...
How much is the strength, the tensile strength?
About 10% of
the compressive.
Yeah.
So it's the same, in the same trend.
Roughly. But we have all the stress-strain in tension. We have the drawing, the stress-strain relationship in tension. I just want to add some...
When splitting starts, it will become immediately.
Yeah.
There's no time.
Of course, we test them under
the
displacement control. Displacement controlled. I just want to add one thing. We do 7 days, 28 days, first day of testing, last day of testing. Each of those, we do 3 samples compression. But at 28 days, in addition to those 3 samples in compression, we do flexural test, beams, 4-point bending, and we do splitting, each one of them 3. So just so we have the proper material testing at 28 days.
Very good.
Okay. Any other questions?
Well, I'm not. For me, what I'm interested in is the approach, and also we identified the materials, what is confinement, what is self-compacting concrete, what is steel tension test, what is the what is ductility, what is a lot of things we have learned through this presentation. Whether the specific topic of the PhD thesis or research is of interest for the usual or my friend engineers everywhere, but it's a very interesting topic, and I think we learned a lot from your presentation today, Professor. Thank you.
Thank you. Thank you. I hope this is the amount of PhD, and this is representative of Wollongong University.
Yeah, it shows the amount of work that a student does to get his PhD. We would like to see you again on this channel.
Yes, of course.
But this time I would like to have you in a theoretical or practical topic from inside the engineering
no problem
syllabus or engineering studies.
No problem.
We started with the PhD research, and that's fine. I think this time let's talk about, for example, if you have time, we talk about buckling as a topic.
Of course.
Or pressure vessels, if you like. I don't know what you were working before. I remember you were specialized in optimization.
Yes.
Yeah.
Still, optimization is in my blood.
Yeah.
I had 2 PhD students worked on optimization. 2? No, more than 2. 3 worked on optimization.
Well, that's also a nice project or subject if we talk about, for example, using optimization for specific topics in civil engineering, non-linear, linear. How do we deal with conditions? I think we should teach people. We should teach ourselves and people some theoretical ideas next time.
Of course.
Yeah.
Of course.
I'm very glad to have you here, sir, and good evening for you, in fact. And I will go and have a sleep for a couple of hours. I go to work.
Thank you very much.
Yeah.
Thank you.
Thank you very much, sir. Thank you very much, Professor.
Thank you. Thank
And
you.
thanks for everybody for watching this. Bye-bye.